Okay, Yesenia, Dominic, are both of you ready?
Yes.
Yeah, I'm ready.
Real quick, do we have the screen recording going already or no?
Yes.
Okay, can you see the presentation screen?
Yes.
Yep.
Okay.
Okay, so we are going to be doing a literature review. We chose analog computing and deep learning. You want to move to the next slide. So what is deep learning? So it's a subset of machine learning and AI that is based on artificial neural networks as pictured here to the right, where there are multiple layers of data processing. It imitates how human brains work and how we learn new information. For example, speech, images, and text. AI uses multiple accumulate functions or MAX, which at first was done by the central processing unit, but then machine learning grew rapidly when GPUs or graphic processing units were used. They perform operations faster than CPUs, however, use floating point arithmetic, which is beyond the needs for machine learning. So now we're getting to a point where we can no longer increase the number of MAX integrated on a chip unless we keep decreasing the number of bits they use. And they use too much power. So now they're looking into using analog computing to be used for deep learning. It combines computation and memory, where digital transfers data from memory to the CPU every time a computation is done. So this means it consumes less energy, and it also increases the speed of the computations. So how is this going to be used in deep learning? So some ways that it's used is using matrix operations and also a crossbar resistor array. So if you move to the next slide. So some problems though with digital that we face with deep learning is that it does consume a lot of power, as I talked about earlier. It is slower and we're starting to get to that point where we just can't expand and improve anymore to be used for AI. So some problems we face with analog, however, is it's not easily scalable. It's more difficult and time consuming. It's limited to that noise floor. It is affected by other external factors, unlike digital, that include heat and noise. And it's not as easy to debug as digital is.
Okay, so to kind of build on that, we talked about how digital computing kind of has a certain limitation in terms of the efficiency. And we can kind of see that on the graph on the right. This is a graph of the computations per joule, or the efficiency over the years. And it maps the processing units, whether it's CPUs or GPUs. And it kind of follows the Moore's law trend that we're all kind of familiar with. And we kind of see that it all kind of levels out as the years go on, and it reaches like this efficiency wall or the power wall. And we look at the top and we see that this is the next generation application need. This is what the machine learning AI is going to kind of require for more complex tasks in the future. And we can kind of see from this discrepancy that the trends aren't going to meet the application need. So something really has to change. And this power wall kind of serves as a roadblock for the increasing demand, power demand, and efficiency demand for AI. So the hope is for analog computing to be able to increase the power efficiency and to be able to meet the application need. And in doing so, we would have faster operations and the ability to handle more complex cases. And a little example about this is our brain. Our brain kind of processes millions, billions of calculations and such, and it only expends about 25 watts of power versus other advanced GPUs or advanced technologies use up a lot more for 200 for significantly less amount of calculations. That's really kind of what our goal is, to be more efficient with these calculations, the amount of power that they expend. So the objectives for this project is to basically conduct a literature review and show if it's possible to be able to use analog computing over the current methods currently employed. And so we're going to kind of examine the efficiency of using analog computing techniques over current general purpose ones. We're kind of going to go over the feasibility of using computing over digital circuits, how difficult is it going to be, what roadblocks we have to overcome in order to do so, and finally determine how scalable these techniques will be and if it's going to be able to meet the future needs for AI.
Okay, so for our preliminary literature review, we looked up a few examples of companies that have used old analog technology to create these chips to solve these problems that we were just discussing. And the first example is this Toshiba AI accelerator chip. This is an analog chip that was made to carry out multiply accumulate functions that we mentioned previously. And this function accounts for the vast majority of neural network operations. And this chip does so by controlling oscillation times and frequencies of an oscillator circuit. And it can do operations in the phase domain, and that's how it achieves the multiply accumulate function. And they can also use this for multiplication, addition, and memory operations, all while consuming only 1/8 of the power of a comparable digital circuit. And so far, Toshiba has used this chip for image recognition and anomaly detection. If we go to our next slide, we also have resistive RAM, which is a type of memory created by an array of variable resistors. As you can see on the right is an image kind of showing how they build these. And the resistor value varies based on the voltage applied to it, and you can apply negative voltage to get rid of that value. And the goal and reason they build these is to allow for computations to be done inside of the memory, which cuts down on the bottleneck that normal digital computers face of having to fetch and store data from the memory and then do computations and then store it back. And so the resistive RAM can do all these things with higher switching speeds and much less power draw than other current storage devices. And one thing to note is you can add analog to digital converters at the end of these arrays so that they can be used alongside digital devices. So potential applications for analog circuits are to be used alongside digital circuits as well, so they don't have to be a complete replacement. And if you go to the next slide, we also did a review on some charge trap transistors, and these transistors work by trapping charges as they say, in basically a high K metal gate, which just means it's a high dielectric constant. So it can hold a lot of charge, and they can use these charge traps as a type of memory. And charge trap transistors can be used as analog multipliers, and that these multipliers, when compared to digital versions, have a much higher efficiency with an even smaller area size as the digital ones. And on the right, you can see a fully connected multiplication array. And these array of multipliers can form a computing engine in the images. And this company has built a neural network by using many of these arrays to classify images of several handwritten digits. And they achieve that with much higher efficiency and smaller area, as mentioned before. And that's it. So for our schedule, we plan to use the first 1 to 3 weeks on research and more literature review, take a deeper dive into the topics that we discussed. Then the next 2 weeks, we are going to work on drafting our paper. Then after that, 2 more weeks to work on the presentation. Then finally, the last week, we will do our presentation and submit our paper. And our 3 focus areas are power efficiency, scalability, and usability. So again, our goal here is to perform a literature review. Goal is to determine how analog computing can be used for deep learning, whether that be fully replacing digital circuits or working alongside them. We will also want to determine if it's a viable solution moving forward and what issues arise from using analog circuitry versus digital circuitry. And here are all of our references we used.
Does anyone have any questions?
I have a question, I think. I don't know if you've gotten far enough in your research yet, but why haven't these techniques been used yet in actual settings? Do you guys know yet or not?
I would say just from what I've seen so far, I think because it's so difficult, because we've been so focused on digital, because it's just easier to use, that people have kind of stopped using analog. So now that they're getting to that point of, oh, we're kind of stuck now that's why they're looking back into it. But it's a challenge, and it is that, is it really worth it or not? And yeah, still looking into how they're doing that.
Okay, thank you.
Any other questions? Okay, if not, then I think that ends our presentation and we can move on to the next set.
I think our group is next.
Okay, yeah, so just share screen and
Yeah, let's figure this out.
start.
All right. 1 second, Zoom is in the way. All right. Hello, everyone. We're the Smart Grid group. It's consisting of me, Kim Fullenkamp, Adriano, and Mohamed. We're doing a literature review, and the topic we'll be introducing you to today is big data in smart grids, and what that means in terms of analytics techniques and processes, and that must be utilized, as well as the topic of security within that scope. So first we have our introduction. As everyone else, we have our motivation, our topic name, our goal. Then we have our current literature works. Then we have our outcome, which includes insights, limitations, things like that. Then our conclusion, then our references. So our motivation. The emergence of the next generation power system known as the smart grid means there's a lot of new techniques and issues that come with it. Our main topic, as you can see, is the application of big data analytics processes on the smart grid and a study of the resulting security risks concerns and eventually the solutions to that. So what exactly does that mean? As we know, big data is basically just a huge quantity of data sets in various data types. And due to the large volume and number of data types received from the power grid, a high level of analytics is involved and required. And that stuff can affect marketing, engagement strategies, and even peak load considerations. And here's our current works.
For the current works is big data in smart grid. First is about the applications. First one is situational awareness, and the pictures explains that. For example, this concept does exist in airplane industry first, and is about like the data is going through 3 steps. First one is perceptions, then comprehension and projections. After that, a decision will be made, and can be made by human. Sometimes it has to be made in a millisecond, so it has to be by the software or something. And then the action to the system. So if we have a big data there, the decision can be more accurate and precise. The second one is a state estimation. And in smart grid, we have power system state estimation, which is a solve the iteration due to the nonlinear measurement in smart grid. And when the big data does exist, we have a new method called decoupled Newton linear estimation, which is using the time sequence of the data, and that helps to accelerate the process of estimation. The third one is event classification and detection. In smart grid, we have like multiple sources of the data for the voltage, frequency, and the load. And because of this, so we need to like to classify the event and then detect the location. So for example, we have like voltage drop. So we classify that as a voltage drop, and then we detect the location. For the technologies, we have Hadoop and Spark. Hadoop is used for a static data, but is not suitable for the real-time data. So, however, we have a Spark, which is able to process real-time data and the online data, which is and also indeed it's in the memory is 100 times faster than Hadoop. For the analytics process, we have data acquisition and data processing. In the next slide, we have challenges and future prospects. The first one is multi-source data integration and storage. So the data is in smart grid is not from a single domain. The data is like multiple sources of the data. So we have to do like the formats and the representation for the data, because we have different types of the data. The second one is a real-time data processing technology, which is because of multi-source of the data, and these data are going through like a mathematical complex. It's complex equations, so it has to be like the response has to be in a millisecond, and because there has to be a delay and a latency for the response. The third one is the data compression, and the next one is big data visualization technology, which is we have visualized the graph and chart for the data, but in smart grid we have multiple sources of the data. So we have like frequency, the voltage. So we have it's kind of, and it's change constantly. So we have to, it's a little bit a challenge to represent them for visualization. The last one is data privacy and security, which is simply leakage. Private data is leakage, and the security is cyber security.
All right, next we have security. Security is a big deal. The smart grid holds a lot of consumer data like names, addresses, billing information, your network information, all of which could be used maliciously if it falls into the wrong hands. All of that together, you could get your money stolen, a lot of bad things. Utilities in general are a significant target to cyber attacks, as it can be debilitating for a large network of consumers if these hackers or these cyber attacks could get it. And there's a lot of vulnerable components and spots of attack, such as consumers themselves, a weak network security, and even power line communication, such as between the power companies and meters and stuff like that. In a database system like the smart grid, even false data injection, for example, could have devastating effects, where basically cyber attacks will change certain information, and then predictions and billing and all kinds of things can be thrown off, even producing outages and things like that if you've got voltage information wrong. The graph here shows several predicted attack sources from 2016 to 2018. It includes items such as IoT vulnerabilities and even corporate level offenses. So what's the solution to this? That's something that our group will be exploring throughout the course of this literature review.
For the literature review, we're going to be going through the things that we can do with the big data analysis. Specifically, like we were saying, outage management, which means we can, with big data models, we can react quicker to outages and redirect power to affected areas a lot faster than if we were to manually calculate everything and change everything with the current systems that we have, especially getting all that generation from the companies that are actually generating power. If we have, you know, large storage centers like the smart grid proposes, then it's a lot easier to redirect power from non-responsive areas to areas that are requiring that power. The next thing is renewable energy forecasting, which lets us store energy more reliably and power more reliably. We can make models with energy collection data to have a model for when we have peaks and valleys and data in energy production, and how we can distribute that better, basically more efficiently to where energy needs to go, especially during peak loads. Like we were saying with cybersecurity, the customer protection and loss is very important. Having a predictive network or having a predictive model for specific areas for certain customers, for certain users, we can detect when some things could go astray. If there was a foul play and like a false data injection, like Kimberly was saying, that could be used by companies to either track the meters into seeing if they're a victim to false power data, basically, so false metering, or if they were doing that for themselves, which means that companies could then go after them for fraud, and it would make the whole process a lot more orderly, I suppose. Power quality assessment is simply analyzing the disturbances in power. Like Mohammed was saying, there's voltage and current data that are tracked, and those data points all make a specific system that is already in place, and it has to change, a little bit every so often. So if there's ever these big disturbances, we can track that. We can follow how that could affect the system. And then finally, future market developments, which is just power market stuff. With all the voltage, or with all the energy selling data, we can make financial models for certain prices for power at certain times from certain companies, which should make the power market a lot cheaper for everyone and a lot more reliable for everyone. So in conclusion, more management, or proper management and analysis of this big data and how we make models from it can give us incredibly accurate predictive models, which can be used from all the things that I said earlier, but also requiring more data for those more accurate predictive models means inherently more risk. The more data you collect, the more risk there is of that data being leaked or being used for, being used by the wrong people, essentially. So our schedule, pretty simple. We're in week 2. This is our proposal, our very basic proposal. Next 2 weeks, we'll be doing more research into this. And 2 weeks after that, we'll be doing our first draft of the paper. We'll have our final draft by the end of November, and then our presentation should be the very start of December. And Kim is going to be focusing on the security and the cyber attacks. I'm going to be focusing on modeling application, predictive modeling, and Mohammed is focusing on the technologies aspect of smart grid. And those are our references. And I think that is everything. So
Does anyone have any questions? We'll give it a minute, and if not, we can probably just move on.
I'll ask a question, I guess. Why were you guys interested in looking into smart grids? And what sparked your interest with the whole group?
Probably because it's definitely the next step in, I mean, power is important. We all need power. As more technology, everyone needs power as we progress. So smart grids are definitely the next level of that. Right now, sometimes power companies don't even know if an outage is going on. Like they'll have to be called in. So a smart grid, especially with all that data coming in, will definitely help people and power companies know and answer that more efficiently, and even save money for customers.
the other thing about the other big thing with smart grids is at least my interest in it is renewable power, especially. It makes it a lot easier to integrate storage solutions for renewable power, especially because we need to start moving away from the greenhouse gas producing powers like coal and natural gas, stuff like that. So smart grid integration makes it easier for renewable integration, and they're kind of intermingled. It's definitely the next big step that we have to take for cleaner energy or cleaner power, and not killing the planet, I guess.
Okay, thanks.
Any more questions? All right, we can probably give it to the next group.
Hello everyone, my name is Omar Al-Louaihi, and today our group, Mu'tasim Al-Abri and Mohammed Al-Maskri, are going to do our presentation about electrical car. First of all, let's move to next slide to my introduction. First of all, what do you think, guys? What is an electrical car? Electrical car is a one powered by an electrical motor rather than the traditional petroleum, and it has rechargeable batteries that can be charged by electricity at home. And what do you think, guys? Which come first, electrical car or gas car? For sure, electrical car come first, and it's found on 1834, and it's come long before gasoline car. And electrical car is not something new, but it doesn't have like interest in the past, because it has some problem in the top speed and in the range. However, it comes back again in 2008 when Tesla came to change the game of the industry, and it solved a lot of problems about the top speed and about the range. And if we move to another slide, we can see that electrical car has both benefits and problems and challenges. And the first, the benefits, electrical car has like, it's good for the environment and it's cheaper to run. And also we don't need a lot to fix on it. However, there is like some problems in years. For example, we have to change the battery after 5 to 10 years to the batteries works officially, and also it's take too long to charge, and also maybe you have hard times to find the point charger in the whole country. However, if we move to next slide, we can see that there are many companies that interest in electrical car, and Tesla is one of the most important company that develop the electrical car, and it's one of the beginner, and it's one of the first company that focus on electrical car. And to know more about the process and how the electricity inside the car, Al-Mu'tasim will explain that for you.
Yes, so I'll talk about the electrical cars and how they run. So before we move to Tesla, we need to talk about the features of electrical cars in general. As we know, electrical cars use electricity to run, so it is friendly to the environment, and it has like no emissions or pollutions, such as like air pollution or noise pollution. Also, electrical cars has more smooth and quiet ride. So there are so many companies besides Tesla that is improving and trying to invent a lot of new things in electrical cars. So there are Ford and Hyundai and also so many other companies. Oops. So how does the electrical cars work, or how does Tesla cars work in specific? So as we see in this picture, Tesla cars has three main parts: the back part, the middle part, and the front part. As we see in this picture, the back part has three main parts. It has the inverter, gearbox, and the induction motor. In the middle here, we have the power supply, which is lithium-ion batteries, and in the front we have the radiator for this car. So we'll talk about how each part of them works. The inductor or the induction motor has two parts on it. It has the stator and the rotor. The stator it comes inside it, the rotor. The rotor is the part that is moving. So how does this part move? It has a coil around it. So the electricity goes to the coil, which make a magnetic field, which make the rotor moves. So where does this coil get power? It gets it from the batteries. As we see here in this picture in the middle, the batteries provides the coil with the power source. So as we know, the batteries produce a DC power, and we need to convert it to AC power. Here where the inverter job comes. So the inverter works as a brain in this car. So it converts the DC power to AC power so the rotor can run. And here we have the gearbox. Gearbox is attached to the induction motor. The gear moves the power from the induction motor to the wheels so the car can run. So as the battery is running, there will be a high heat on them. In Tesla cars, there is something called glycol coolant. It's a subject placed between the batteries so to cool down the temperature in the power supply, and it is attached in the front of the car to the radiator. So next number.
Now we will compare electrical cars and petrol cars. First of all, technology. Petrol cars uses IC engine. It converts fuel into temperature, energy, and pressure to move into the pistons. The force is produced and are never in uniform. It has multiple mechanical balancing issues, and the engine is not self-started. So this makes the energy very heavy. On the other hand, electrical cars uses battery packs with inductor motors. Is the quite opposite. They rotate with the power with the help of electromagnetic fields. So it's easy to control the motor speed just by adjusting the frequency. Therefore, an induction motor is lighter, at the same time more powerful, as you can see in the photo shown next to the slides. Second of all, can you go back? Cooling system. Cooling system. The IC engine produces high amount of waste energy, where inductor motors has less amount of energy. Therefore, the car does not require any source of cooling mechanism. Third comparison, the energy density. Petrol cars has much higher energy density. With energy density devices, it increases the friction of the tire and the road, which makes taking a turn in a corner is much difficult. While electrical cars has smaller energy devices installed, this makes the turning energy much easier. Fueling time, refueling. Petrol cars is an disadvantage here because petrol cars are an advantage here because it takes only 5 minutes to fill the car with fuel. However, the electrical cars takes around an estimate of an hour. The travel costs. Petrol cars can estimate of $0.1 per mile, while electrical car only costs $0.03 per mile, which is 1/3 cheaper. They also have a lower lifetime maintenance costs compared to the petrol vehicles. And lastly, power. For electrical cars, a single speed transmission is used for the car. Therefore, the speed is controlled easily. It is controlled by the inverter, as Mu'tasim previously explained. It's simply by just adjusting the output power frequency. This was the key role of revival of electrical cars. They can also produce a great torque even at the start. while IC engines will struggle at low RPM. Moreover, the control over the torque can be controlled instantly, where IC engines has the slowest response time compared to the inductor motors. This also adds a better traction to the car. And from the next slide, in conclusion, we realized that electrical cars has better, cheaper, and more safer for the environment and for the user, because it does not use any petrol and it doesn't pollute the air. And it also has an AI installed, but we did not research about it yet. So that would be on our future researches. It will help develop the car even better for the future. Do you guys have any questions?
Yeah, I have one question.
Sure.
Are you guys are you guys going to do any research or talk about the infrastructure requirements on electrical systems or electrical car systems? Because they are very good, but that's always been the issue, is the having that infrastructure of being able to use it wherever, just like we have gas stations anywhere.
Yeah. We're planning to research about it, but we don't know yet. Like we didn't read about it yet.
No, that's fair.
Other questions? Okay.
Okay, I think that's, if there's no more questions, we're pretty much ready to end this meeting here. Just good job, everyone. Everyone's presented under 15 minutes, so we had no issues there. So yeah, that's it. Thank you, guys.
Yeah.
Have a great day.
Yeah, you too.